Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. So, in the last lecture we were discussing about the turbulence models. We have derived the basic equations for turbulence, we have seen the Reynolds equations, and then we have seen that the complexities for solving the turbulence flow problems. Since we have got 4 equations in 3 dimensions, we have got 4 equations, 3 momentum equations and 1 continuity equations, but we have got generally 10 unknowns. So, it is very difficult to get a mathematical solution for this turbulence problem. So, we have seen say by considering these various methodologies for a solution for turbulent flow problems. So, we have discussed about 5 models for the turbulent flow simulations. First one is zero equation models, which we have seen last time, and second one is the 1 equation model, and the third one is 2 equation models, and fourth one is stress equation models, and fifth one is larger D simulation models. So, now out of these 5 models which are generally used, which is available in literature. So, as the turbulence problems are very complex, it is always better to go for a complete solution or the either larger dissimulation or complete equation models, but even the solution of this is very complex, large computational capacity is required, and then now recent times we have got number of computational fluid dynamics packages which can take care of these kinds of models. But to in this course, but to understand the fundamental theories or to the principles of turbulence, in this course we will be discussing one of the model, the first model, zero equation models. Since by it this equation, zero equation models are derived based upon some of the experimental observations and then some of the empirical theories. So, it is a mix of some of the experimental observations and some of the empirical equations. So, in this field, so in the zero equation models, 2 names are very important. They have developed this theory. There, one is Prandtl and another one is von Karman. So, the zero equation model briefly will be discussed here for the turbulence flow simulation, and that will give a wider picture of how difficulties are these problems, and then how we can approach with a simplified theory. So, out of this first one which we are discussing here is the Prandtl's mixing length theory. So, this Prandtl's mixing length theory is based on the concept of mixing length using the analogy of mean free path of kinetic theory of gases. So, kinetic theory of gases has been well developed in the beginning of 20th century, and then Prandtl used this kinetic theory of gases to analyze the turbulent flow for simplified cases like a flow or a parallel plate and then flow through pipes. So, that some aspect of the turbulence or say the theories behind turbulence can be understood. So he started with the kinetic theory of gases. So what he did is he defined a length called mixing length, which is the average distance perpendicular to flow a small fluid mass will travel before its momentum is changed by new environment. So here this is explained in this figure. So first one is the case of laminar flow, the velocity distribution profile is given, and second case is for turbulent flow. So as per Prandtl, by using the kinetic theory of gases, what he found is, say, he defined a length called mixing length, and then this length is actually the average distance perpendicular to flow a small fluid mass. Say if you consider lump of fluid or a small fluid mass, it will travel the average distance which travel perpendicular to flow before its momentum is changed from one environment to another environment or a new environment. So this is clear from this figure. So if you consider a small mass here, this one, and then it is jumping to other location, say 2, so that the momentum is changed in this process. So this length Prandtl defined as mixing length, and then he proposed the mixing length hypothesis, which is known as the one of the fundamental development in the area of turbulence. So then he defined the shear stress due to turbulence as tau is equal to eta into del u by del y, where u is the velocity in x direction, and where eta is equal to at by subscript t by y, where at is the ratio of mixing coefficient. So he also used this Boussinesq approximation, which is given by eta is equal to at by y, where y is the vertical distance, at is the ratio of mixing coefficient. So by using this further, say as shown in this with respect to this figure, y is in this direction and x is in this direction, and velocity for the turbulence is plotted, and then he derived the shear stress as the tau is equal to minus rho u x dash u y dash bar. So this is the definition of the shear stress. And by using the Boussinesq hypothesis, by considering a parallel flow, Prandtl showed that this ux bar can be written as a function of the ux y, and he considered us is equal to 0, and uz bar is equal to 0, and uy bar is equal to 0. So what he considered here is, you can see it is a parallel flow. So in the parallel flow case, say for example, if you consider plate like this, and then he considered parallel flow such that for this particular case the velocity variation, say if this is x direction and here this is y direction, so that x variation is with respect to ux and y only, and other components like the z components and the y components are 0. So this is how he defined a problem. If this is a parallel plate and then flow over a flat plate, and he considered the parallel flow such that ux is the velocity in x direction is a function of y, and us and the velocity in z direction and y direction are 0. So he considered such a problem, and then he tried to explain the turbulence happening with respect to this particular problem, and so that further the theory can be extended for other problems. So for this parallel flow, say along x direction for which the longitudinal velocity is ux, this depends on lateral location of y only. So as we have already seen here, this ux depends on only y, so that the flow is other components are 0. So this is the parallel flow which Prandtl considered to explain the turbulence. So that this rho u dash x u dash z mean, or it's rho u x dash u z dash bar and minus rho u y dash u z dash bar is equal to 0 for this particular parallel flow case. So that he derived tau is equal to the shear stress is equal to minus rho u x dash u y dash bar, that is equal to eta del u x bar by del y by using the Boussinesq hypothesis. So finally Prandtl got this the shear stress is equal to minus rho u x dash u y dash bar is equal to eta del u x bar by del y as given in equation number 5, and then Prandtl suggested a method to calculate this tau, from which we can find out this eta. So, that is the way he approached the problem. And finally, Prandtl introduced a concept of the mixing length, which is called mixing length hypothesis for the fluid which travels laterally before losing its momentum and acquiring a new momentum in the new layer. So, by Prandtl's hypothesis, the mixture or mixing length, the absolute value of the fluctuating component of velocity along x axis is given by u x dash bar is equal to L into the mixing length multiplied by the derivative of u x by the derivative of u x with respect to y, or mixing length multiplied by du x bar by dy. So, this L is equal to Lm, that is the transverse distance where the lump of fluid mass is say jumping or traveling, that distance is called the mixing length or the mixer length. And then, so in all this problem, our final aim is to find out an expression for the velocity. So, he used this theory in with the Boston's approximation, and then finally the fluctuating component as shown in this figure, he wrote if it is u y dash bar, he showed that this u y dash bar is proportional to u x dash. So, that we can write u y dash bar is equal to a constant multiplied by u x dash. So, this constant, this u x dash, as we have already seen, u x dash bar can be written as mixing length multiplied by du x bar by dy. So, finally, we can write this u y dash bar is equal to a constant multiplied by L into du x bar by dy as given in equation number 7. And for the particular case of the parallel flow, as we have explained here, for this particular case, Prandtl finally showed that this u x dash u z dash bar is equal to u y dash u z dash bar is equal to 0, and such that the apparent shear stress tau is equal to minus rho u s dash u y dash bar is equal to eta into del u x bar by del y. And from the kinetic theory of gases, from which he has started this, he has derived this theory, eta is equal to rho L u x dash bar. And finally, we can write by using this here, we can write by using 10 in 9, we can write to the shear stress tau is equal to rho L square into du x bar by dy all square. So, where L is mixing length. So, this finally we can write this is equal to, so taking the sign into consideration, we can write tau is equal to rho L square du x bar, the modulus of du x bar dy into du x bar by dy. So, that the sign is taken care as shown in equation number 12. So, this is finally say what Prandtl did is say he used the Boston's approximation, and then he used the kinetic theory of gases such that the shear stress is say approximated, or shear stress is described in terms of the mixing length square multiplied by the density, and then the square of the gradient of the velocity in y direction, or du x bar by dy whole square. So, that is finally he got this expression. So, now using this equation number 12, say this equation is the resultant of the Prandtl's mixing length theory, as we already discussed. Equation 12 is the resultant of Prandtl's mixing length theory. So, now this mixing length theory, as you can see in equation number 12, here you can see here this includes the fact that the apparent shear stress due to turbulence will change sign with the velocity gradient. So, that is obvious from equation number 12, and by Prandtl mixing length hypothesis, the apparent shear stress can be calculated for the non mixing length L as tau is equal to tau 0 into 1 minus y by r 0, that is equal to rho L square du r by dy all square. So, if you consider say with respect to the parallel flow, even if we consider the pipe flow as shown in this slide here. You can see that this R0 is the radius of the pipe, and then if y is we are taking from the bottom of the pipe, and velocity can be plotted like this. So, if we consider this in comparison with the pipe flow and the parallel flow which Prandtl considered. So, here we can write tau is equal to tau 0, that means the shear stress on the boundary tau is equal to tau 0 into 1 minus y by r 0. So, that is equal to this tau is equal to tau 0 into 1 minus y by r 0, that is equal to rho L square du bar by dy square. So, this is in comparison with the pipe flow as explained here. So, finally, by using this in comparison with the pipe flow, we can write this mixing length L is equal to square root of tau 0 by rho divided by du bar by dy into square root of 1 minus y by r 0. So, this is obtained from this previous equation. So, we can write tau the mixing length L is equal to tau 0 by rho by du bar by dy into 1 minus y by r 0. So, this is obvious from this figure. So, now, from this, say once we determine the shear stress or the boundary shear stress, we can get the velocity variation we can calculate, and then other parameters can be calculated. So, this we will be explaining further in the next few slides, how this mixing length hypothesis can be further used to calculate the velocity distribution and various other parameters. So, before going to the further applications of the mixing length hypothesis proposed by Prandtl, this von Karman also just who was working with Prandtl, he further modified this mixing length hypothesis and then this shear stress calculation as shown in here. So, what Karman did here is he approximated this through various experiments and through various observations. Von Karman showed that the apparent shear stress due to turbulence in a parallel flow can be written as tau is equal to rho into kappa square dux bar by dy all to the power 4 divided by d square ux bar by dy square all square. So, this is the equation derived by von Karman, and he put forward a constant called kappa, which is for this particular parallel flow which he derived, but finally he has shown this kappa is valid, which has got a value of 0.4. So, he derived this kappa within terms of the shear stress in terms of this kappa, and this kappa is called Karman constant, having a value of generally 0.4. So, now in comparison with by using the mixing length theory also with further experiments and observations, von Karman showed that the shear stress can be expressed as rho into kappa square dx bar by dy to the power 4 divided by d square ux bar by dy square all square as shown in equation number 13. And now, if you compare this equation number 13 and then if you compare equation number 12. So, this is equation number 12 here, this is equation number 12 which is derived by Prandtl, that is equation number 12, and then the equation derived by through experiments and observations derived by von Karman, equation number 13 here, this is equation number 13. Finally, what von Karman did is he derived an expression for the mixer length or mixing length, which is we can write as Ly, which is the mixer length or mixing length is equal to kappa into dux bar by dy divided by d square ux bar by dy square as shown in equation number 14 in this slide. So, finally, the Prandtl's mixing length was used by von Karman, and with his own observations finally he derived an expression for the mixing length. So, once in most of the problems, once we know the mixing length and then we can calculate other parameters. So, that is the importance of this Karman's approach or Karman's hypothesis here. So, finally, he derived an expression for the mixing length or mixer length as given in the equation number 14. So, this is now both Karman's theories as well as Prandtl's mixing length theory we can use together such that once the mixing length is determined, we can go for the calculation of the velocity or shear stress and other parameters if some parameters are already available with respect to some measurement. So, that is the application of this mixing length hypothesis and Karman's approach. So, now in the next few slides we will be discussing about the applications of this, but here before proceeding to further applications, with the Karman's approach which we have seen here, you can observe here Karman assumed the turbulent flow patterns are similar in the neighborhood of any two points in the flow, and they differ only in their length and time scale. So, this is an important observation put forward by Karman. So, he assumed that turbulent flow patterns are similar in the neighborhood of any two points in the flow, and they differ only in their length and time scale. So, this is obvious from this figure here. So, this figure in this slide you can see as per the Karman's approach, and then he also suggested that say the Karman's model for the mixing length, which we have already seen in the previous equation, it is a point function. We can observe that it is a point function and depends only on the velocity distribution in the vicinity of a particular point. So, this is one of the important observation which we can get from the Karman's approach. So, that means this mixing length is a point function, and it depends mainly on the velocity distribution in the vicinity of the particular point which we consider in the turbulence flow regime. So, that is one of the important observations which we can see from the Karman's model for mixing length. So, now further in the next few slides we will discuss how this mixing length theory and Karman's approach can be further utilized to solve various problems. First we will see the flow over a flat plate or parallel flow case further, and then we will be discussing about the pipe flow. So, the first has written here the application of the mixing length theory. So, for the velocity distribution in turbulent flows. As mentioned, our main purpose here is to find out the velocity distribution in the turbulence flow regime. So, as we have seen earlier in some of the cases for turbulence flow, the total shear stress, we can see that in most of the cases even the turbulence is generated, especially when we consider the flow over a flat plate. There is even the most of the flow regime is turbulence, but there can be a small layer called a laminar sublayer. So, when we consider the shear stress at any particular level, then we have to consider we can split the shear stress into the shear stress due to the turbulence and the shear stress due to the effect of the laminar nature or laminar sublayer. So, the total shear stress can be written as tau is equal to tau turbulence plus tau laminar, as in here in this equation number 1 further. So, tau laminar is the shear stress due to the dynamic viscosity of the fluid, as you can see as the flow takes place, and here the tau turbulent is the additional apparent shear stress due to turbulence. So, the total shear stress is the effect of the shear stress due to dynamic viscosity of the fluid, and then the additional apparent shear stress due to the turbulence. So, now this tau laminar, as we have seen, we can use the Newton's law of viscosity and write tau laminar is equal to mu into dx bar by dy as written in equation number 2, and tau turbulence, as we have seen the mixing length theory, we can write tau turbulent is equal to rho L square into dx bar by dy, its modulus into dx bar by dy as shown in equation number 3. So, the total shear stress is the effect of this equation number 3 and equation number 2, tau laminar and tau turbulent. So, once we know the magnitude of the total shear stress and the mixing length. So, as I mentioned here, we are trying to use the mixing length which we have discussed already. So, by knowing the magnitude of the total shear stress and the mixing length, it is possible to solve this equation number 1, that means the shear stress. So, it is possible to solve equation number 1 for ux, that means our aim is to find out the velocity for ux and thus get a relation for the velocity distribution in the turbulent flow. So, this way we are proceeding to solve the turbulent flow. So, if we know the magnitude of the total shear stress and then the mixing length, so what we can do is we can solve for the velocity ux and then we can get a relation for the velocity distribution in the turbulent flow. So, as we have already seen in the Prandtl's mixing length hypothesis. So, Prandtl assumed that the mixing length L is linearly proportional to the distance y from the boundary with a factor say called kappa to be determined from experiment. So, finally, he put forward by using this linear theory, linear proportionality by putting L is equal to kappa into y, where kappa is the Karman's constant which we have already seen. So, the mixture length L is equal to kappa into y as in equation number 4. So, as we have Karman in the Karman's approach which we have already seen earlier and shown by Karman. So, von Karman L is equal to mixture length is also equal to kappa into du x bar by dy divided by d square u x bar divided by dy square as shown in this equation number 5. So, by using this, so for a flow along a solid boundary, so as you can see in this slide, so when we consider the flow along a solid boundary, you can see that there are three regions. One is the laminar sublayer, as I mentioned initially, there is a small sublayer which is called a laminar sublayer, and then we will be having a transition, and then we will be having a turbulent flow. So, we can see that in the laminar sublayer the viscous shear predominates, so that we can see that the velocity is proportional to this distance y. There is somewhat a linear variation. So, this is this area where it is laminar flow, say due to all the laminar sublayer, and then there is a transition zone from laminar to turbulent, and in the turbulent flow you can see that this transition zone is called buffer zone, where viscous stress and Reynolds stress are same. So, this is the transition or buffer zone, and then the turbulent zone you can see that the Reynolds stress are much larger, and then here you can see that the velocity is proportional to the natural logarithm of the distance y as shown here. So, these are the variations say with respect to the laminar sublayer, the buffer zone or the turbulence. So, this we can show experimentally also. So, now if we use so when we discuss the velocity variation within the turbulent flow, we have to consider this zone separately, the laminar sublayer or the turbulent zone separately, and then for the laminar sublayer, the region near the boundary, we can write by using the Newton's law of viscosity, we can write tau is equal to mu into du x bar by dy, and away from the boundary we can use the as far as shear stress is concerned, we can use the Prandtl's hypothesis in combination with the Karman's approach given by tau is equal to rho L square du x bar by dy into du x bar by dy as shown in equation number 7. And then transition zone is concerned, it is what is happening is the transition takes place from laminar to turbulent, it is known as buffer zone. So, two velocity distribution near boundary governed by equation 6 and equation away from the boundary governed by equation number 7. So, this is a combination in the buffer zone, it is a combination between equation number 6 and equation number 7, since transition takes place from the laminar sublayer to the turbulent region. So, the two velocity distribution should be connected suitably, so that one gets a continuous velocity distribution from the boundary to within the flow. So, due to the complexity, the problem is so complex that we cannot just clearly identify how this transition is taking place. So, generally what we do in the laminar sublayer region, we know the variation, say it is generally u is proportional to the distance y, and then the turbulent zone, the u is proportional to natural logarithm of y as we have already seen, and then in between what we have to do is the two velocity distribution can be connected suitably, so that we get a continuous velocity distribution from the boundary to within the flow. So, this is the procedure which is generally adopted. And now this real velocity we can define as u star is equal to square root of tau turbulent by rho. So, this we have already discussed earlier. So, we can define a term called shear velocity, which is equal to square root of tau turbulent divided by rho or this is a shear stress term divided by rho is square root, equation number 8. This is also the shear velocity, also called as friction velocity sometimes. So, this is actually the characteristics of turbulent fluctuating motion. So, the shear velocity or the friction velocity, it is actually the characteristics of the turbulent fluctuating motion. So, we can define as U star is equal to square root of tau turbulent divided by rho, and then the shear velocity on the boundary, we can say y is equal to 0. So, that we can write U star O is equal to square root of tau 0 by rho as given in equation number 9, where tau 0 is the shear stress at the wall or boundary. So, here we introduce the term shear velocity or friction velocity. Actually, it is a characteristics of the turbulent fluctuating motion. So, this way these various parameters are now defined, and then if you know either the mixing length or say the shear stress or some of the parameters, then we can determine the velocity. So, it is just like now the zero equation model or the Prandtl's mixing length is directly not giving a complete solution, but it is we can use it in combination with some of the measured values or with some of the other observations. So, that is generally this theory. So, now we have already discussed the Prandtl's mixing length hypothesis. So, what are the advantages, what are the disadvantages? So, in the next 2 slides we are discussing what are the advantages. So, this Prandtl's hypothesis has been put forward at the beginning of the 20th century. So, you can see that at that time the turbulence phenomena, what is happening in turbulence or how the velocity variation, all these things were totally unknown. The understanding of this turbulence flow was very little for the scientists and engineers. So, at that time when Prandtl proposed this theory, it was actually one of the important observation as far as this turbulent flow, which has put forward or which has boosted the development of various flying mechanisms like development of aeroplanes and other kinds of machines. So, that is one of the important theory in as far as turbulent flow is concerned. So, some of the advantage of this mixing length hypothesis, here you can see, and the merits say this theory is simple and can be used with some degree of accuracy. So, you can see that we can easily explain, we can easily understand this mixing length hypothesis. It is not so complex like as we have seen the Reynolds equations or the complete turbulence theory is concerned. Mixing length theory is much simple, and even though it is not totally correct, completely accurate, the accuracy is less, but still we can use this mixing length hypothesis with some degree of accuracy, so that many of the problems can be solved, or we can easily understand how the system is working to certain degree of accuracy. So, if appropriate the choice of mixing length L is made, we can get a good solution. So, this depends upon how effectively we can get the we can calculate the mixing length, or we can find out the mixing length. So, as we have already seen, once we have derived a term for the shear stress in terms of mixing length and the velocity gradient. So, if the mixing length can be correctly obtained through various means, then we can calculate other parameters accurately. So, this depends upon the mixing length. So, one of the important advantage is that this the theory is simple and can be easily used with some degree of accuracy for various turbulent flow problems. And then if delta is the thickness of turbulence region in y direction, then some appropriate value for mixing length is available in literature through various measurement. So, for example, if L by delta is equal to L by delta is equal to 0.07 for plain mixing layer, L is equal to 0.09 for plain jet in stagnant environment. Like that, say if delta is the thickness of the turbulence region in y direction, then we can say from various observation we can write the mixing length divided by delta. Some values are available in literature. So, these are some of the important advantages of the Prandtl's mixing length hypothesis. And some of the disadvantages. So, here as I mentioned, this is say this Prandtl mixing length theory is based upon some of the experimental observations and some of the empirical relationship and some of the theories at that time. So, some of the disadvantages, the mixing length hypothesis does not consider diffusion or convection of turbulence. So, as we have seen the turbulence, the nature of turbulence, this diffusion and convection are very important process in turbulence. Actually, in the mixing length hypothesis which we have seen here or proposed by Prandtl's, this it does not consider the diffusion or convective turbulence. So, this is actually one of the major disadvantage of demerit of the mixing length hypothesis. And also mixing length hypothesis states that effective viscosity does not exist where velocity gradient is 0. So, this is also one of the disadvantage. So, as written here in this slide, even though mixing length hypothesis is widely used even now. So, say as due to the limitations of this mixing length hypothesis, say let say some sophisticated analysis will be taken over the mixing length hypothesis. So, nowadays say with very complex CFD computational fluid dynamics packages are available to critically analyze most of the problems. So, generally this mixing length hypothesis or this is used for preliminary analysis for various problems, but otherwise since we have got very good computational software or computational fluid dynamics packages where this all these various equations, momentum equations or Reynolds equations are taken care. So, we can get a better solution. So, but still we use this mixing length hypothesis for preliminary analysis and then understanding of the turbulence process. So, these are the some of the advantages and disadvantages of the mixing length hypothesis put forward by Prandtl. So, now in the next few slides and we will be trying to use this Prandtl's hypothesis as well as various other theories to derive some equations for the variation of the velocities by considering first flow over a flat plate or a parallel flow, and then we will be considering the turbulent flow through pipe. So, first case is velocity distribution for a parallel flow within smooth boundaries. So, as we have seen in the region away from the wall, we can write by using the Prandtl's hypothesis, we can write tau is equal to tau turbulent is equal to rho L square dx bar by dy all square, equation number 10, and then by using Karman's approach, mixing length is equal to kappa into y. So, if we put forward this here, so that we can write tau is equal to rho kappa square y square du x bar by dy all square as shown in equation number 11. So, here we are considering the parallel flow with smooth boundaries. So, Prandtl introduced one additional relation for shear stress in that it remains constant. So, that is tau is equal to tau 0. So, that we can write say this equation number 11 here, we can write here 11 can be written as equation number 12, tau 0 is equal to rho kappa square y square dx bar by dy all square as in equation number 12. So, now as we have seen here we have defined a shear term called shear velocity. So, which is tau 0 is equal to rho u star o square, where rho is the density, u star o is the shear velocity. So, tau 0 is equal to rho u star o square. So, now if we substitute for this rho u star square here in equation number 12, so that we can write u star o square is equal to kappa square into y square into du x bar by dy all square. So, that is equation number 13. So, finally, by using this here we can write du x bar by dy is equal to u star o by kappa into y as in equation number 14. So, now here our aim is to get an expression for the velocity variation. So, we are using the Prandtl's as well as Karman's approach, and then dx bar by dy is equal to, we got a relation, the variation of the velocity with respect to y as dx bar by dy is equal to u star o by kappa y as in equation number 14. So, now we can solve this equation number 14 to get a solution for the velocity. So, as I mentioned, our aim is to get an expression for the velocity. So, we can write u x is equal to u star o by kappa into log E y plus c. So, by solving equation number 14 here, we get u x is equal to u star o y, which is the shear velocity divided by kappa into log E natural log y plus c, where c is a constant of the with respect to the integration. So, now this equation number 15 indicates that the velocity varies logarithmically. So, that we have already seen in the turbulence region the velocity varies logarithmically. So, now the constant integration we can determine from the condition that a turbulent velocity distribution must fit in the laminar sublayer in the vicinities of the boundaries. So, we have already seen earlier that there is, so we have here you can see in this figure there is a laminar sublayer and then the turbulence. So, with respect to this, so here this constant of integration we can determine from the condition that the turbulent velocity distribution must fit in the laminar sublayer in the vicinities of the boundary. So, now if you assume that the shear stress remains constant and it is equal to tau 0 on the boundary, and assuming further that dx bar by dy is equal to say the derivative of the velocity with respect to y direction, we can approximate as u x by y. So, that we can write tau 0 is equal to mu into u x by y, but we have already seen this tau 0 is equal to rho into u star o square. So, that we can write u x by u star o is equal to u star o into y by nu, where nu is the kinematic viscosity. So, this is valid for the near to the boundary. So, equation number 16, u x by u star o is equal to u star o into y by nu. So, hence we can write equation number 16 gives the velocity distribution in the vicinity of the boundary. So, that this is linear. So, that is we can say it is on the laminar sublayer. So, in equation number 15 velocity is not 0 at y is equal to 0, if not this c is equal to 0. So, here equation number 15 is here. So, you can see that in equation number 15 this velocity is not 0 at y, is actually the velocity should be 0 due to no slip condition y is equal to 0. So, this is possible only unless c is equal to 0. You can see equation number 15 here, and then you can see that velocity is not 0 at y is equal to unless c is equal to 0. So, this is explained, all this what we are discussing here is explained with respect to flow over a flat plate here. So, the free stream velocity is coming, and here is the flat plate, and then once the turbulence is generated, you can see there is a laminar sublayer, and then the turbulence is taking place. So, say how the transition and then a laminar and turbulent transition, and then the laminar sublayer is explained in this figure. So, now we want to say, as I mentioned, our aim is to finally determine an expression for the velocity. So, the constant of integration c is determined from the condition that the turbulent velocity distribution must join the laminar velocity distribution in the immediate vicinity of the boundary, where laminar and turbulent shear stresses are of the same order of magnitude. So, here you can see this is the laminar sublayer and then turbulence. So, to determine this c, the velocity distribution must join the laminar velocity distribution in the immediate vicinity of the boundary where laminar and turbulent shear stress are of the same order of magnitude. So, that we can write this y is equal to, we can put y is equal to y dash, where u x is say a small value or u x is tending to 0 in equation number 15 here, here is 15. So, then we can write c is equal to, the constant c is equal to minus u star o by kappa log e y dash as in equation number 17. So, here now equation, so now by using this c we can write equation number 15 as u x is equal to u star o by kappa log e y minus log e y dash as in equation number 18. So, now from equation number 16 one can write that such a velocity distribution exists up to a distance delta dash, that is proportional to nu by u star O, and this delta dash may be taken as representing the thickness of the laminar sublayer. So, this is the laminar sublayer. You can see that a small sublayer called a laminar sublayer. So, that is actually may be taken as representing the thickness of the laminar sublayer. So, the distance y dash and delta dash may be expected to be independent. So, that y dash is tending to delta dash. So, that is also approximately equal to nu by u star O as in equation number 19, and y dash we can represent as a constant multiplied beta into nu by u star. So, as in equation number 20. So, where beta is a numerical constant. So, if we substitute this here in equation number 18, our previous equation number 18, we can write the velocity variation u x is equal to u star O by kappa into log E y minus log E beta into nu by u star O. So, now from this, by simplifying, we can write we can get an expression u x is equal to u star O by kappa into log E u star O into y by nu minus log E beta. So, that is equation number 21. So, as we can see, this u star O into y by nu is a Reynolds number based on the friction velocity or the shear velocity u star at a distance y. So, this term is actually a Reynolds number based on the friction velocity. So, for smooth boundaries at high Reynolds number, you can see that this is already in this region u x is equal to u star O by is equal to u star O into y by nu as given in equation number 16 for laminar sublayer earlier. So, that finally, for the turbulent region, we can write u x by u star O is equal to 1 by kappa log E natural log E or u star O into y by nu minus log E beta as explained in equation number 23. So, this equation number 23 as shown here, this equation number 23 is called is known as dimensionless logarithmic universal velocity distribution law for smooth boundary. So, when we consider smooth boundary, so this equation is called a dimensionless logarithmic universal velocity distribution law. So, this constants kappa and beta are empirical, we can determine through experiments already. Say we can see kappa is almost equal to 0.4, which is a universal constant. Kappa is equal to 0.4, and beta also we can determine. Beta depends on the roughness at the boundaries of the for the particular case we consider. So, for low Reynolds number, we can show that instead of this linear variation, we can show that power law is valid, which is expressed as u x by u star O is equal to c into y into u star O by nu to the power n, where c and n are constant as shown in equation number 24. So, this is for a low Reynolds number flow. So, this you can see, this slide shows how the velocity distribution takes place. So, this is this is the wall, and then the schematic representation, say outer turbulent zone and then laminar sublayer, and how the shear stress is varying is shown in this figure, which is taken from the Wiley and Streeter fluid mechanics book. So, now for rough boundaries, so we have seen how the variation taking place for smooth boundaries. So, if we consider a rough boundary, you can see that say the boundary, the roughness of the boundary also affect the flow. So, that this laminar sublayer thickness which we have seen earlier, for rough boundaries we can write y dash is equal to alpha into epsilon, where this epsilon is the roughness coefficient or roughness factor, and alpha is a constant. So, that now by using our earlier equation number 18, we can write u x by u star O is equal to 1 by kappa log E y by epsilon minus log E alpha, equation number 26. So, this equation number 26 represents universal velocity distribution law for rough surfaces. So, we have already seen a universal velocity distribution for smooth surfaces. So, now equation number 26 gives universal velocity distribution law for rough surfaces. So, this equation number 23 and 26 yield another law called universal velocity defect law, which is true for smooth and rough boundaries. So, if we consider u x is equal to u max at y is equal to h, then we can write U max divided by U star O is equal to 1 by kappa log E U star O into H by nu minus log E beta as in equation number 27. So, that we can write, say if you consider the velocity is to be maximum at y is equal to h. So, that U max x by U star O is equal to 1 by kappa log E h by epsilon minus log E alpha as in equation number 28. So, if you subtract this equation number 23 and 26, this 23 here 23 and then here the equation number 26 from equation number 27 and 28, you will get U max minus U x by divided by U star O is equal to 1 by kappa log E h by y, and this is called the universal velocity defect law, which is valid for both smooth and rough boundary. So, finally, through this say we got a general expression which you can use for say smooth boundaries as well as rough boundaries. So, that equation is U max minus U x divided by U star O is equal to 1 by kappa log E h by y. This equation is called a universal velocity defect law, which is applicable for smooth as well as rough boundaries. So, this is the general expression. Before going to the pipe flow, we will discuss a small example. So, here the example problem is, say in a meteorological station, the wind velocity was measured at 2 points 3 meter and 6 meter above the ground. The values obtained being 2 meter per second and 2.3 meter per second respectively. We had to compute the shear velocity U star O, assuming Karman constant kappa as 0.4. And then what is the probable laminar sublayer thickness for the problem. Next part of the question is what is the velocity at 9 meter above the ground, assuming the boundary is smooth and take kinematic viscosity nu is equal to 0.145 Stokes. So, for this particular problem is concerned, say this is in a meteor station where the wind velocity is measured. So, we know the say from the ground level the velocity is measured at 2 points 3 meter and 3 meter and 6 meter above the ground, and we know the velocities values 2 meter per second and 2.3 meter per second respectively. So, now we know the kinematic viscosity and then we know the Karman constant kappa, and assuming the boundary is smooth, we have to determine the velocity at 9 meter above the ground, and then we have to determine the probable laminar sublayer thickness and the shear velocity. So, the problem we can just explain like this in this figure. So, if in the meteorological station here you can see that if this is the ground level. So, here we have 3 meter, then 6 meter and 9 meter. So, here the velocity is given as 2 meter per second, here 2.3 meter per second. So, we have to determine the velocity at this 9 meter location. So, to solve this problem, we will say use this equation. So, the velocity distribution for smooth boundary, we have given seen the equation U x is equal to U star O by kappa into log E y minus log y dash, equation number 1 in this slide. So, now we will take the ground level as origin. So, here at y is equal to 3 meter, it is given U x is equal to 2 meter per second, at y is equal to 6 meter, U x is equal to 2.3 meter per second. So, we will substitute these values to this equation number 1. So, 2 is equal to U star O divided by k into log E 3 minus log E y dash, and 2.3 is equal to U star O by k log E 6 minus log E y dash, equation 2 and 3. So, now we can solve this equation 2 and 3, we can get the shear velocity at U star O as 0.173, and then say the shear stress you can see from this slide, tau 0 is equal to rho U star O square, equation number 4. The laminar sublayer thickness, say actually Richards has measured this for this kinds of problem the laminar sublayer thickness, he found that generally it will be between the u star O by into y by nu is between 0 to 5. So, here y is the laminar sublayer thickness. So, now we will see that the Raychard's observation, and then we will also calculate the laminar sublayer thickness from our earlier equation, in this equation number 1. So, and then we will compare. So, now let us take y is equal to, let us just the thickness of laminar sublayer thickness in the Raychard's observation here. So, that delta star is equal to phi nu by u star O. So, by solving this expression, we will get the delta star as 4.19 into 10 to the power minus 4 meter. So, now we can from the equation 2 here, this equation 2, since u star we have already found kappa is known. So, now we can for this real problem we can also find out the laminar sublayer thickness. So, if we solve that equation, we will get y dash is equal to 0.029 meter. So, you can see that what Raychard's observed is say lot of difference is there. So, but here we got y dash or the laminar sublayer thickness as 0.029 meter. So, now to calculate the velocity, since now the constants, the unknown parameters here u star O is already determined. So, we can find out the velocity at 9 meter. So, we will use this equation here, the earlier equation here, equation number 1. So, from that if you substitute, you will get u x is equal to 0.173 by 0.4 into log E 9 minus log E 0.029. So, that you will get the velocity as 2.48 meter per second. So, this is a small example. So, similar way different kinds of problem, especially for turbulent flow or related to flat plate or similar kinds of problem can be solved. So, next we will be discussing the turbulent flow through pipes, initially through some say smooth pipe and then rough pipes.